The objective of this video is the following. We'd like to be able to write the electronic configurations of atoms and ions up to an atomic number of 36. And secondly, we'd like to know the first two exceptions to what's called the Aufbau principle. Those two exceptions are chromium and calcium. Okay? So basically at the end of this presentation, you should be able to answer this kind of a question. Which of the following represents the correct electronic configuration of calcium between these crazy things? Which of those is the correct configuration? At the end of this video, you should be able to answer that. So let's get started. In a previous video, we had described what's called the orbit model of electronic configuration, in which electrons are arranged in these sort of planetary orbits. But we said this model was not sufficient to explain certain phenomena. So we moved on to the orbital model. Within the orbital model, each energy level here is made up of a bunch of sublevels. Okay, here we have one sublevel, two sublevels, three sublevels, and four sublevels there. When I say each energy level is made up of a bunch of sublevels, I really mean each energy level apart from the n equals 1, because n equals 1 just has one sublevel. Okay, so we have that there, and we know that it keeps going on, 5, 6, 7, and G, HI, or FGHI. The important thing is that the energy does not only increase as we go 1, 2, 3, 4, it also increases SPDF. Okay, and we can remember that order by thinking electrons are speedy flies, SPDF. Now, the orbitals come into play when we break down these levels further down into what are called orbitals, and we represent them as squares, even though that's not the real shape. Okay, so here we have one square, so therefore one orbital, then three squares there, 5 and 7. That's just an odd number sequence there. Okay, and still revision, we said that each orbital can house a maximum of 2 electrons. We also said that the electrons have up and down spin. We said it was a special kind of spin, a quantum spin, but you don't have to really understand what that means. So we said that an electron's address can be described in terms of 4 things: the main energy level or shell, the sublevel SPDF, the orbital. The orbitals have special names for P, D, and F, but you only have to know the ones for P, so X, Y, and Z. And finally, in terms of the spin, that is the up and the down spin. Okay? Now, we filled up this whole array of orbitals kind of without thinking about what kind of atom would actually have this many electrons. We've just filled up, what is this, about 64 electrons. But what we really want to do in this video is go one electron at a time and see where would electrons want to go if they're filling up shells basically one by one. How are we going to arrange the electrons one by one? What do I mean by that? So let's take some element here in the periodic table. Let's take hydrogen. Hydrogen has one proton, which means it also has one electron. Which orbital is the electron going to land in? Or which orbital shape is it going to assume? It's going to be here. Okay? How about the next one? Helium. Helium is going to come in there. So helium has 2 electrons in the 1s orbital. How about lithium? Lithium has 3 electrons because it has 3 protons. What does that look like? It'll have this 1s2 full, and then it'll fill up here a 2s1. Then beryllium would have 1s2 full, and then a 2s2. Then boron will move into the 2p. We have now those 5 electrons, 1, 2, 3, 4, 5, to match the atomic number of boron. How about carbon? Carbon fills in there. How about nitrogen? There. Oxygen? There. And on like that. But what are the rules that I'm using to fill up those electrons? How do I know the way in which the electrons get arranged? That is the focus of this video, okay? A quick reminder though, that we're going to be drawing lots of squares in this video, but electrons are not arranged in squares. Remember that we had explained that these squares are just representations of actual 3-dimensional objects, which we call orbitals. We said that the s squares, or the s orbitals, are spherically shaped. Okay, they can contain 2 electrons like every orbital. Okay, here we had demonstrated how we fill up the electrons for oxygen. So we have 1s2, then 2s2 in the larger sphere. Then we have the 2p electrons in these dumbbell shapes, okay, the dumbbell shapes. And we have the x, the y, and the z, and we filled in that last electron there into this x. This should be an x there, okay. That's just a reminder. So we're going to be drawing lots of squares, but what we really are representing are 3D shapes of high probability chances, or high probability of finding electrons. So let's finally get started. That was all revision. I think now we can get started. What we need to get started is a basic rule. What is the rule for filling in electrons? It's a very simple rule. Here's the rule. Electrons like to go into lower energy orbitals first. What do we call this rule? We call this rule the Aufbau principle. Aufbau, what a nice word. If you Google translate Aufbau, you see it means construction. How do we build up the electrons into their orbitals? Now, if they're going in the order of low energy first, to figure out how to fill these in, we need to figure out which orbitals are lower energy and which are higher energy. And we had said that generally speaking, the bigger numbers are higher energy than the smaller numbers. And we also said that F is higher energy than D, which is higher energy than P, which is higher energy than S. So we need some way of ordering them. What we're going to do is we'll take away this diagonal line, we'll put a straight line, and we're going to raise up the P to represent the fact that they have higher energy than S. We raise up the D, we raise up the F. So let's go ahead and do that. So the P gets raised up, D gets raised up, and F gets raised up even more. It falls off our screen. Okay, let's get rid of our title so we can see the F. And then let's also add in a bunch more. We add in the S's and the P's. Now this order here represents the energy levels, or the energy trend in terms of increasing energy of these sublevels now. Okay, so if we draw arrows connecting each of these sublevels to the y-axis, we can deduce the order of increasing energy. And there's the order there: 1s, 2s, 2p, then 3s, 3p, then 3s, then 3d, then 4p, and on like that. You're never going to just remember this picture, so you need some mnemonics to help you. There are two ways to figure out that order. The first is called the Madelung diagram, and the second is called the periodic table. I'll show you the Madelung diagram approach, and later on I'll show you the periodic table approach. Let's start with the Madelung diagram. You should remember the Madelung from the previous video. But basically we have the S's, right, there in a column, then the P's, then the D's, and the F's. I think in the previous video I didn't draw these ones. So you don't really need to think about those ones for now, or for the IB really. You just need to focus on these first four rows. So it goes 1s, then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Now here's the trick. Here's the trick, okay? If we stab through this Madelung diagram, we can get this order of increasing energy. So we stab through, and we stab through again diagonally. We stab through again diagonally. Stab through, stab through, stab through, stab through. And that gives us this order here. So we go 1s, 2s, okay? 1s, 2s. Then after 2s, we get what? 2p. 2p there. Then 3s. 3s there, okay? Then 3p. Then 4s. Then 3d. And on like magic, okay? With the Madelung diagram. All right. Now, that's full enough. We don't care about those ones at the moment. Let's just get to writing these electronic configurations, which is what we're here for. Okay, there are going to be many questions like this on the exam, so make sure you get this down. Let's begin. I'm going to put the Madelung diagram here and the periodic table down here. And now we're going to break up the periodic table into 3 blocks. The S block here, okay, and helium actually really belongs in this block, so I'll just write He there. Okay, so we have the S block, then the P block there. As you can see, helium doesn't belong in the P. Helium is just there because it acts like a noble gas, therefore they put it up in period 18, but it really belongs here. Okay, so we have the P, and then we have the D, this group of 10 elements in the middle. So we've broken up our periodic table into 3, the S, the P, and the D. And this will help us to fill in electrons. Here's the idea. We're going to take the big number for our electronic configurations from these periods here, 1, 2, 3, 4, and we take the letter and the superscript from the position in the block. Probably sounds like gibberish to you. Let's look at an example. Hydrogen. Hydrogen is in period 1. So we take its big number from that period. So hydrogen will be 1. Okay. Then its letter from the position in the block. So it's in the S block, which means it must be 1s. And it's the first position in the S block, so 1s, 1. That is how we write the electronic configuration for hydrogen, 1s1. Okay, there you have 1s1. How do we draw it? We just put the S square, okay, and we put that up arrow or down arrow, it doesn't matter. Okay, as long as the other one is in the opposite direction. Let's move on. Helium. Helium, we said, belongs here. Okay, so it'll be period 1, position 2 in the S block. That's 1s2. Okay, and how do we draw it? Just like that, with two opposite arrows. Next one, we move on to, what's the next one? Lithium, right? So for lithium now, we filled in the first period, so 1s1, 1s2, we filled in that. So we need to put that in. And then we do 2s1, period 2, first element in the S block, 2s1. So period 2, S block, first element, 2s1. How do we draw it? Just like that. Okay, next one, let's keep going. Beryllium. No, not next one. I need to explain to you what the Pauli's exclusion principle is. So here we had lithium, 1s2. Why didn't we just do 1s3? Why did I do 1s2, 2s1? Well, because only 2 electrons can fit in an orbital. We know this, right? We know this already, but it has a special name. It's called Pauli's exclusion principle. You can remember it because this guy, he looks a little bit like a strict teacher. And he's the kind of teacher that would say not more than 2 people on one desk. Pauli's exclusion principle, not more than 2 people on one desk, okay? And there's the principle there stated simply. Only 2 electrons can exist in a single atomic orbital. Okay, so now we have lithium. We move on to beryllium. Beryllium will be what? 1s2, 2s2, and we draw it like that. Carbon, what's carbon like? Sorry, not carbon, boron, 1s2, 2s2, and then now we're in the p block. So how do we figure out that valence electron for the p block? We have period 2, p block, therefore p, so it would be 2p, first element in there, so 2p1. Okay, so boron would be 1s2, 2s2, 2p1. And that's what that looks like. Remember that the p sublevels have 3 orbitals, the x, the y, and the z. So each of those can contain 2 electrons. But you don't have to, I don't think you have to label these if you're asked to draw the configuration of boron. Okay, we move on to carbon. So carbon, similarly, will be 1s2, 2s2, 2p2. We put that second electron there. The next one, nitrogen, 2p3. And oxygen, 2p4. We put that next electron there. But let's pause. Because wait a minute. Why didn't we put, so here we went from boron here, 2p1 to 2p2. Why didn't we just put the second electron here? And then do that, and then do that, or so on like that? Well, because electrons, they don't like to be squeezed together. They like to spread out. This principle, this spreading out principle, we call it Hund's rule of maximum multiplicity. What is that rule? It states that electrons occupy orbitals singly before they pair up. Okay? Electrons occupy orbitals singly before they pair up. You can remember it by thinking, this guy, his name Hund, it sounds like 111. No, wait, how can you remember it? Nitrogen here looks like 111, okay? And so that is obeying Hund's rule. If we didn't obey Hund's rule there, we would have put it here. We would have put a second electron there. But it's obeying Hund's rule, and it looks like 111. So it looks like the number 101. 101, Hund's rule of maximum multiplicity. If you don't like the mnemonic, yeah, you don't have to take it, okay? All right, we move on to fluorine now. And it's the 5th element in the p block, period 2. Therefore, it's 2, period 2, p5 for the 5th element, okay? And of course, neon looks like that with 2p6. We keep going. Next period, period 3. We start with sodium. Okay, 1s2, 2s2, 2p6, 3s1. Why is it 3s1? Because now we're in period 3. It's the first element in the S block. So 3s1. Okay? And of course, I've been using the periodic table, but you could have been using the Madelung diagram to deduce the same thing. You just need to remember that these guys have 1 orbital here, 3 orbitals, 5 orbitals, and 7. And if you want, you can duplicate that to get the number of electrons. So you have 2, 6, 10, and 14. And you could use that to deduce those. Let's do it for sodium quickly. So we have 1s2 there, 2s2 there, then 2p6. Remember, we have 6 electrons can fit in here, and then 3s1. Okay, let's move on. The next thing we need to discuss is something called the difference between a full and a condensed or abbreviated electronic configuration. And we'll also describe the difference between writing and drawing an electronic configuration. What is a full versus condensed? This thing we just drew for sodium, that's a full electronic configuration. What is a condensed one? There's a condensed one. In order to condense a configuration, you're going to take the last noble gas. That is the last configuration in this group there. For this one, sodium, it would be neon, right? Because we have neon here, and then after neon, we move over to sodium. Okay, so we group all of that neon's configuration into one and just squeeze it and put it between these square brackets here and call that neon. Okay, and then we put the other stuff. That's how to condense. You just condense to the last noble gas and only include the valence electrons after the noble gas configuration. Okay, so that's how you do a condensed one for sodium. For magnesium, that's how you would do it. Okay, so now with magnesium, we're at 3s2 or neon 3s2. Okay, aluminum, we move on to the p block. We're still in period 3, 3p1. Okay, or neon 3s2, 3p1. Now the distinction between write and draw, if you're asked to write, all you need to do is just this part here, okay, or this, depending on whether it's condensed or full. But if you're asked to draw, then you should do both the text and these boxes. Okay, they ask you to draw the electronic configuration, do the text and the boxes. If they ask you to draw the shapes of orbitals, please don't draw these squares. These squares are not the shapes of orbitals. It's only if they ask you to draw the electronic configuration that you draw these. The shapes of orbitals, you draw the sphere and the dumbbell things, okay? These are just representations. All right, let's move on. Now we move on to, so we stick with the condensed one. We move to silicon. What does silicon look like? 3s2, 3p2, like that. Second element, third period, p block. Therefore 3p2. Second, third period, p block. Okay, then we move on to phosphorus. It's getting boring now. Sulfur, chlorine, and then argon. Okay, next period. This is the exciting period. So potassium is argon 4s1, nice and easy. Then calcium is argon 4s2. How about scandium? Is it going to be 4s2, 4s1 since we are in period 4 there? No. Here we need to fall down. We need to fall down. So we go from 4s to what? To 3d. So 4s2 to 3d1. Okay? And you can get this easily by looking at the Madelung diagram. After 4s2, you get what? 3d. So 4s, then 3d. Not 4s, then 4d. That would be jumping. Okay? 4s, then 3d. So we fill in the 3d there. Scandium, 3d1. Then titanium, 3d2. Vanadium, 3d3. Chromium we'd expect to be what? 3d4, right? Why not? As we're just filling it in, following the Aufbau principle. But no, this is an exception to what seems like an Aufbau principle. What is the exception here? The exception is the following. This is a wrong configuration because the electrons like to have a whole sublevel fully filled, okay? And the distance between 4s and 3d is quite little. And so that electron is going to jump to the 3d shell. And you end up with 4s1, 3d5 instead of 4s2, 3d4, okay? You can see that the distance between 4s and 3d is so small, okay? That electron can easily make that leap across in order to make it look nice. Look how nice and pretty it looks, okay? So the electron likes it to look nice and pretty like that. So it jumps over. It has something to do with electron stability and on and on. But you don't have to know the reason, you just need to know the effect, okay? So There's chromium there now, is 4s1 3d5. What is manganese going to look like? We fill in now that missing electron there, 4s2. How about iron? We just fill in normally, okay? Iron, cobalt, nickel, they all look the same. We get now to copper. This is another of those nasty ones, okay? We would expect it to be 3d9 because it's the 9th element in this 3D block, right? But again, this electron doesn't like this arrangement. It wants to jump across, and so it does just that, okay? So it jumps across because this D shell is particularly stable, and it prefers that configuration. And then the next one, so zinc would then fill in the 4s2. Okay. Now, how can we remember that copper and chromium are exceptions? Here's a mnemonic for you. You can think of a crooked witch. A crooked witch. Crooked witch. Crooked witch. So chromium and copper are trying to fill up the D subshell. Chromium, copper, D subshell. Chromium, copper, D subshell. Copper there, that electron jumped to fill up the D subshell. Chromium, copper, D subshell. Okay, zinc looks like that, 4s2 3d10. As you can see, it has a nicely filled configuration there. Then we move on to what? To gallium. For gallium, we need to ascend the hill again. Okay, so here we fell down, here we go up. So from 3D, we go up to 4p. Or if you're looking at the Madelung diagram, then it's obvious that we go from 3D to 4p. Okay, but if you're looking at the periodic table, you need to remember to ascend. So we have 4p1, then 4p2, 4p3, 4p4, 4p5, and we are done with 4p6. Okay, that was nice. Very nice. Let's expand now. For the IB, you only need to know up to a configuration of chromium there, a Z of 36. But let's just expand so you have a general sense of what the rest of them look like. So we had said that first we fill in this first period here, 1s1, 1s2, then 2s1, 2s2, 2p1, 2p blah, 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 then 3s1, 3s2, 3p1, 3p2, and so on. Then we get to 4s. We remember to fall down. We go from 4s to 3d. Then we jump up again to 4p. We come here, 5s, fall down to 4d, go up again to 5p. Here we get to 6s. You might expect maybe we go here to, I don't know, 6d or 5d, but no. Listen to what we do. We go to the F block, okay? If you remember the Madelung diagram, the next lowest sublevel after 6s is 4f. So we go and fill in the F sublevel before we come to this 5d and 6p. And therefore, a real representation of the periodic table looks like that. But of course, we don't draw it this way because it would be too tiny. You'd never see the actual numbers or letters in there. Okay? So that's the big picture for you. This is extension. They're not going to ask you that on the IB. What they will ask you on the IB, though, is the following. Write the electronic configuration of chromium. How do we do this? Here I'm going to use the Madelung diagram method. For chromium, I need 24 electrons since I have 24 protons there, the Z number. So to do my Madelung diagram, I write 1s, then 2s, 2p, then 3s, 3p, 3d, okay, then 4s, 4p. I don't think I have to go this far, but I do it anyways, 4f. Now let me change my color and write the number of electrons I expect in each of these. Here I expect 2 electrons per orbital. Here, 6 electrons. Here how many? 10, right? Remember we go basically 1, 3, 5, 7. And so to figure out the number of electrons, we just double these. Okay, so 7 times 2 will give us 14. All right, now let's figure out Z of 24. We start out with the 1. 1s2. That's our maximum there, okay? Then we move on to the 2s. I forgot my spears. I forgot to stab through. Stab through diagonally. Oop, have I made a mistake? Let's be patient. Make sure I don't stab through wrong. Oh, yes, that's our stab there. Okay, all right. So 1s2, then 2s2, of course. Then what? 2p, 6 electrons can fit in there. Okay, I move to the next line. 3s, 2. Okay, then what else? 3p6, 3p6, and then 4s2. All right, 4s2. Let's count. How many do we have so far? We have 4 there plus 6, so we have 10 there. Then here we have what? Again, 4 plus 6, so another 10. So we have 4 more electrons to fill in, okay? And we are at the 4s now. So the next thing would be the 3d. So we go now to 3d, 4 electrons. And we are done. No, we're not. We're not done, right? Because this 3d4, remember, the 3d4 looks like that. Oh, let's see, I'm making a mistake. It looks like that. And the electron doesn't like it to look like this. It wants to jump over that one. Oh, sorry, it looks like this without this one. So this guy's going to jump over in there. All right, so 3d4 would be without this. And because chromium is one of those crooked exceptions, that electron will jump over here to give us a 3d5, 4s1. And now we are really done. Now we move on to phosphorus. Here they ask us to draw the condensed configuration, and they specify electrons in boxes for phosphorus. For this one, I'm going to use the periodic table method. So first we locate phosphorus on the periodic table. We see it there. It has 15 protons. Therefore, we need to have 15 electrons. Okay. And we're going to use the periodic table method. Remember that for the periodic table method, we just imagine that helium is really here on the periodic table. Okay. And then we can use these groups, the S group here, the P group there, and the D group to draw our configuration. So let's start with this S here. We have period 1, and we have 2 elements there. So we have 1s2. Okay. Then we move on to period 2 because helium is cancelled there. So 2, we have 2 elements, 2s2. Okay. Then we go over there now. We're still in period 2. And we have 6 elements, P block, so 2p6. 2p6. Next up, we go down here, 2 elements, 3s2. And then we get now to phosphorus. So we're in 3 now, okay? And we're in the P block, and we have just 3 until we get to phosphorus, so 3p3. So now we have written it, but they want us to draw it. So how do we draw it for phosphorus? We draw a single box here, 1s2, okay? Then for 2s2, again, we have a single box, 2s2. 2p6, in the P block, we have what? 3 orbitals. Or in the P sublevel, we have 3 orbitals. So 2p6 looks like that. Okay. And then 3s2 simply looks like that. 3p3 will look like that. You have to be careful to obey your Hund's rule. Okay. So we need to put them singly there, obeying Hund's rule of maximum multiplicity. Oh no, it says condensed. So we didn't have to do this. Oh, sorry. So if it's condensed, then you can cancel out all of this and replace it with just neon in square brackets. So we just have neon there in square brackets. Okay, or over here we just have neon in square brackets. And you do the rest. Okay, I was thinking that's kind of a long question. Why they ask me so many boxes? Okay, let's move on to another one. Well, now it's your turn. Which of the following represents the correct electronic configuration of calcium? Pause and think about it. I'm not going to do this question, so it's up to you. Okay, I'll show you the answer in 5 seconds, but make sure you pause the video and think about it. 1, 2, 3, 4, 5. There's your answer. Okay, it's B. So just follow the off-bow principle. Just add them up, 1s2, 2s2, 2p3, and you'll see that this is the right one. Okay, this one is bad. There's too many electrons in the S shell. What's wrong with this one? This one we filled in the 4p before the 4s. It's no good. Just very, very, very bad. All right, so that's the only one possible here. Okay, let's move on. Which of the following represents the correct configuration of chromium? Careful, chromium, the crooked one. Pause and think about it. Pause. 1, 2, 3, 4, 5. Well, the answer must be C. It's not this one, 4s2, 3d4, because it's the ugly one. The electron doesn't like to hang out there when it can fill up that nice D shell. Remember, the D has 5 orbitals, okay, 1, 3, 5, 7, and chromium would look like this if it obeyed the regular Aufbau principle, but it doesn't like that. So that 4s2 is able to make that jump from here over there, becoming a 4s1. Wait, give me a second. Yes, the 4s2 jumps over, making up 4s1, and the 3d4 becomes 3d5. Let's look at another one. Which of these is the correct abbreviated electron diagram for vanadium or vanadium? Pause and think about it again. In 3 seconds, I will show you the answer. 1, 2, 3. There's the answer. Okay? So, this one is wrong because it doesn't obey Hund's rule, right? You have up, down in one. No, they want to spread out. Okay? This one, oh, we took it too far. We spread out too far in this one. Okay? So, this guy doesn't jump unless it's going to make it full. Okay? So, this guy wouldn't jump there unless it would become full. And that would be the case for chromium there. Or for, when I say full, I mean half full there for chromium, or full for copper. Okay, so the answer there is just B. Here's the last one for you. Which group of the periodic table has the following valence configuration? NS2, ND1. This is a weird looking question, but I think you can handle it. Pause, think about it. Pause the video. In 3 seconds, I show you a clue. 1, 2, 3, there's your clue. Which group here would always have blah, 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 S1, blah, blah, P1. Something S1, something P1. It must be group 13, right? Group 13, for example, this element here, which would be what? That would be boron, would have 2s2 and then 2p1, right? So blah, blah, s2, blah, blah, p1, okay? And that one there would be, let's see, that would be aluminum, right? So we have 3s2 and then 3p1. So blah, blah, s2, blah, blah, p1. Okay. All right. I think now that we are done, I was going to go on to ions, but the video is getting long. So let's keep it short here. Okay. But remember, though, that this is one of the more difficult parts of your chemistry career. And so I imagine you might have, if this is your first introduction to this video, you might have understood maybe 50% of it. Okay. Which means you need to go either watch the video again, maybe at a faster speed so you don't have to waste as much time, or you go do practice. Practice is always the best teacher. Okay, so go try out some exercises on the website, perhaps. And I will see you then at the next lesson. Bye-bye.